Okay, in this segment we're going to be interested in looking at the voltage transfer characteristics of a circuit called the source follower. And we're going to be looking at the NMOS version of the circuit, and then at the end we'll look at a PMOS version of the same circuit by way of extension. But this is the MOS analog of the emitter follower circuit. And so we should have some understanding of how it works by way of analogy, but here we have two NMOS transistors connected together like so. We're going to have the drain of the top transistor connected to VDD, positive power supply. The input comes in on the gate of the top transistor, and the output of this circuit is the source of the top transistor. And then the bottom transistor we're going to call the gate voltage VB. And its purpose in life is again to set up a bias current, which we'll call IB, flowing in the top transistor. So we would like for the transistor MB, the bias transistor, to operate as a constant current sink. So this is the bias transistor. And we're going to call this the source follower transistor, MSF. And so we want MB to act as a constant current source, actually sink. And that means that we want MB to be operating in saturation. We're going to assume our standard sorts of things. We're going to assume that the two transistors are matched. Same temperature. And we're going to assume that VA goes to infinity, so negligible early effect. And we'd like to get a handle on what is the relationship between V out and V in. And we'd like to sketch those transfer characteristics. So we're going to do a large signal analysis on this circuit, and we're going to do this with the EKV model, and so it will hold across all levels of inversion. And that's a very unusual thing to be able to do, but it turns out for this circuit we're going to be able to do it. The first thing we're going to need to figure out is what operating mode does the source follower transistor operate in? Is it going to be ohmic? Is it going to be saturation? Could it be either one? If you remember back to our discussion of the emitter follower, the emitter follower, under worst case conditions, was diode connected with respect to being in the forward active mode. If we assume that the input voltage is only strictly within the range of the power supply rails, so that Vn can be at most the positive power supply rail, when it's up at that highest value, then the transistor's base voltage was equal to its collector voltage, and it was basically diode connected. It turns out that for a MOS transistor we also have something we call a diode connection, which is when the gate is connected to the drain. And we would have that same sort of situation if Vin is limited on top by the positive power supply voltage VDD. And that again will correspond to the worst case voltage. That'll correspond to the least voltage across the transistor, and so worst case with respect to the transistor being close to the ohmic region. So if V out, or rather V in, is in the range of, say, 0 to VDD, Vn equals VDD results in the least VDS across MSF. MSF is diode connected in that case. It turns out that diode connected transistors operate in saturation. For any useful current level. And the easiest way for me to show you that is to flip over to here and look at this pair of slides. So this is a figure similar to the ones I've shown you before here, where I've got drain characteristics on a log scale. And this dashed line here is the saturation voltage. So to the left of this curve we have the ohmic region for low VDS, and to the right of this curve we have the saturation region for higher VDSs. And here we have the weak inversion region, the moderate inversion region, and the strong inversion region. This is a slightly different formulation of the saturation voltage. This is the same one as is developed in the MOS transistor packet that you have. It's a little bit different than the one in the slides that I showed a couple of videos ago. But on the next slide here, I have sort of a definition of the diode voltage, or a diode drop for a MOS transistor. So here's the diode connected MOS transistor, and if we sweep the voltage across it and were to plot the current flowing through it, this blue characteristic here is the kind of characteristic we would see. It's just the gate characteristic of the MOS transistor in saturation. It's pretty much identical to that. And what you'll notice is that for most of the current levels that we have here represented, this blue curve lies to the right of this dashed line representing the saturation voltage, which means the voltage on the diode connected transistor, the voltage across the diode connected transistor, is greater than or equal to the saturation voltage, which means the diode connected transistor is operating in saturation. Now, obviously down here, this is approaching a constant roughly 1/10 of a volt, 4 or 5 UT, and eventually for a small enough voltage on the diode connected transistor here, we can make the transistor operate with less than the saturation voltage. That's certainly true. But if you actually work out what kind of current level that corresponds to, that would correspond to a very, very low current level. In fact, it's basically about what we would call reverse junction leakage current in a diode connected BJT. It really doesn't amount to very much current at all. And so that was the origin of my statement that, that the MOS transistor that's diode connected operates in saturation for any useful current level. So any current that's that small is probably not going to swamp out leakage currents, and is not going to represent really a very useful amount of current flowing through our devices. So we're going to assume that our diode connected transistor always operates in saturation. Okay, so what we can do is basically write down how the current we're going to assume that the source follower transistor is saturated. We're going to assume that the bias transistor is also saturated, and we're going to have to come back and see where our assumption about that is going to be self-consistent for the bias transistor. And so we're going to assume the EKV model, which means that for MSF, that implies that the bias current IB is equal to SIS log squared 1 plus e to the kappa, and here we have VG, which is V in, minus VT0, minus, well, VS is V out, over 2UT. And I am off the screen here. All right, let me try that again. EKV implies IB equals SIS log squared 1 plus e to the kappa V in minus VT0 minus V out over 2UT. And also for the bias transistor, IB is equal to SIS times the log squared of 1 plus e to the kappa. Well, in this case it's VB minus VT0 over 2UT. The source voltage is at ground. And so these are equal to each other. And so we can equate the right-hand sides. And we're going to have that SIS log squared 1 plus e to the kappa V in minus VT0 minus V out over 2UT is equal to SIS log squared 1 plus e to the kappa VB minus VT0 over 2UT. Well, so the first thing we notice is that we can cancel SIS because these transistors are matched. We can take the square root of both sides. That undoes the square. We can exponentiate both sides, which undoes the log. You can drop the parentheses. And we can subtract 1 from both sides. And we're left with e to the kappa this stuff minus this stuff over 2UT equals e to the kappa VB minus VT0 over 2UT. And we can take a log of both sides, and that implies that we have kappa times V in minus VT0 minus V out for 2UT is equal to kappa VB minus VT0 over 2UT. We cancel the 2UTs. That leaves us with kappa V in minus VT0 minus V out is equal to kappa VB minus VT0. All the transistors are matched, and so the kappas should be the same, and the VT0 should be the same, and that leaves us with kappa Vn minus Vout equals kappa Vb. And if we rearrange this, we can solve for Vout explicitly. That's going to be kappa times Vn minus Vb. That's a very, very simple relationship. Here we have Vout is just proportional to Vn minus the bias voltage. And so we could sketch that if we wanted to. So I'll just copy that over here. So we have Vout equals kappa Vn minus Vb at all levels of inversion. So we assume the EKV model, which holds for all levels of inversion, and we found a result which holds then for all levels of inversion. And so if we were to sketch this, we'd have plot of Vout versus Vin. Here's VDD. Here's VDD. And let's say this is VB. And here's our identity line. Vout equals Vn. And here, Vout is going to be 0 on this model when Vn is equal to Vb. And it's going to go up from there with a slope of kappa, which is less than 1. Something like that. Now, just like the emitter follower, our model is going to break because our transistor is actually going to be in the ohmic region at some point, and what the actual circuit is going to do is something like this. Right, so it's going to, slope here is going to be kappa. And if we extrapolate this line back, we're going to find that it intersects the x-axis here, the Vn axis, at the bias voltage Vb. And then, we can ask, where is our assumption about this MB being in saturation valid? So where is our starting assumption about MB being saturated valid? Well, in order for MB will be saturated if VDS is greater than VDS sat, or say greater than or equal to VDS sat. Well, VDS is equal to Vout minus 0 for MB. That's just Vout. So that means that MB is saturated if Vout is greater than or equal to VDS sat. Now VDS set is about, say, 4 UT if IB much less than SIS, it's weak inversion, or it's kappa times VB minus VT0 if IB much greater than SIS, which is strong inversion. And it's something kind of starting out at 4 UT and kind of increasing to approach this in moderate inversion. Well, if this is VDS set, that means that our model is valid in this region. Our assumption valid. And using that region V greater than VDS set, we can map that back into, if you like, an allowable range of input voltages. So in this range of input voltages, our circuit is behaving the way that we would like it to. And we can basically use our model for V out as a function of V in to re-express this condition on V out into an equivalent condition on V in. So we can say V out equals kappa V in minus VB. Has to be greater than or equal to VDS set. And so we can then basically divide both sides by kappa and move the VB in. So that condition on V in would be V in is greater than or equal to VB plus VDS set over kappa. So if you like, that is the range of input voltages for which our assumption is valid, and this model, or this analysis, modeling the voltage transfer characteristic is self-consistent. Okay? So, can show you a different set of slides here. So this is basically the same analysis we just did, and that's the result we came to. But on the right here, this is actually some measured voltage transfer characteristics for a source follower made out of 2 ALD1106 NMOS transistors that I took with one of our circuit's SMUs. And I figured I'd just show it to you to see what it looks like with some real data. And you can see here that for this first curve, we have a bias voltage of about 0.7 volts, which is kind of in moderate inversion for these transistors. And you can see that if we extrapolate this curve back to where it intercepts the V-in axis, it's about 0.7 arguably. And 1.2 volts is kind of a strong inversion bias, not super high up in strong inversion. And you can see that the circuit behaves in pretty much the same way. And if we extrapolate this back down to where it intercepts back down here, it's arguably about 1.2 volts, which is the bias voltage. You can see that one of the key differences here is that for the strong inversion curve, the approach to saturation is kind of stretched out some, and so that's why this is a bit rounder here than this one is. This one pops up in about 1/10 of a volt, which is about what you would see for VDS set. Maybe it's widening out to 125 millivolts or so, but it very quickly approaches that kappa VB minus VT0, much more so than it does in this particular case. So, but the slope here is interesting to note. These two lines are pretty darn parallel with each other, and that suggests that the value of kappa is something that is pretty consistent across saturation current levels as you go from weak to moderate to strong inversion. And these lines do look relatively straight, although if you were to actually hold a straight edge up to them, you would notice that they are slightly steeper here than they are down here. There's a little bit of positive concavity here, so that these curves do actually slightly curve, and so if I were to hold a straight edge up to it, you would probably notice that the curve is concave up, and that represents kappa shifting because the depletion layer is increasing in its thickness, and the Cox over Cox plus C depletion therefore is getting closer to 1. So down here, it might be like 0.6, and up here it might be like more like 0.7 or 0.8, something like that. This actually, the source follower characteristic actually turns out to be a nice way to look at and extract the kappa parameter. If you take source follower voltage transfer characteristic here, and you look at where the bias transistor would be saturated, that would be above, let's say here, and you take the numerical derivative of this curve, you can get a good sense of what kappa looks like as a function of the gate to bulk voltage. And actually you can extract some additional device parameters that are used in more sophisticated models for the MOS transistor, like more sophisticated versions of the EKV model that you would find in SPICE, than we are using for hand analysis here, where we assume typically a constant value of kappa. But so that's the source follower characteristic. Now I did briefly want to mention something about the PMOS version of this circuit, and rather than sort of rederiving everything from scratch, I want to show you a way of mapping NMOS results into PMOS results. So for the PMOS source follower, what we would do is take our NMOS circuit and flip it upside down. So let me draw the NMOS version of the circuit here. And to flip it upside down to get the PMOS version, what we're going to do is we're basically going to take stuff that was connected to VDD and connected to ground, and stuff that was connected to ground we would connect it to VDD, and stuff that is up from ground maps into stuff that's true down from VDD. And so here the bias transistor is connected to ground, and so for the PMOS version of the circuit, the bias transistor will be connected to VDD. So this will be NB. Here, the source follower transistor is connected to VDD, and so in our PMOS version of the circuit, the source follower transistor will be PMOS transistor connected to ground. And what we said about the NMOS version of the circuit, statements that we made that were true up from ground, get mapped into statements that are true down from VDD. And so we said that Vout was equal to kappa times Vn minus VDD, rather VB, sorry, for Vn greater than or equal to Vb plus VDS sat over kappa. So for the NMOS version of the circuit, that was true. This one would map into VDD minus Vout is equal to kappa times VDD minus Vn minus VDD minus VB. Okay, so every place we had a voltage, we replace it with VDD minus a voltage. And so we can do some simplification here. We have VDD, right, minus VDD, those cancel, right? And we could factor out a minus sign. And so we would have here VDD minus Vout is equal to, let's say, minus kappa Vn minus Vb. So here I took the minus sign on Vn and the minus sign, let's say, on Vb and factored that out. And what we're going to do is we're going to transpose the Vout and then transpose this to the other side and then flip it around. And so this becomes Vout is equal to VDD plus kappa times Vn minus Vb. Or if you like, we could take this minus sign out and swap the Vn and the Vb and have this be Vb minus Vn. That would be another way of writing it. Here, Vb is going to be a number that's close to VDD, and Vn is going to be a number that goes from, let's say, ground up to some maximum value. So you could write it a number of different ways, but having this be a positive number probably makes more sense. But if you like, you could actually have it flip the other way around. And so our condition here, this one would become VDD minus Vn greater than or equal to VDD minus VB. And actually the VDS sat would become VSD sat. Over kappa. You could put in VDD minus VS, or VDD minus VD minus VDD minus VS, and it would become VD, be a minus VD, and a minus VS, and that becomes VSD. The VDDs would cancel, and so I just kind of did that in one step. Something interesting happens here, though. So if you'll notice, if we drop the parentheses, which we can do here, we'll have a common VDD that we can add or subtract from both sides of this inequality. And that makes these go away. And we have a minus Vn greater than or equal to minus Vb plus VSD sat over kappa. Well, what we would like is to basically have this minus sign go away. And so we can multiply both sides of this inequality by minus 1. But you have to remember that when you multiply both sides of an inequality by a negative number, that will flip the sense of the inequality. And so multiplying by minus 1, we get Vn less than or equal to VB minus VSD sat over kappa. So here we have our PMOS model, and here we have the condition for its validity, just basically mapped directly from the analogous NMOS characteristics. So without having to go through the EKV model and writing down the log squared 1 plus e to the x over 2, yada yada yada. To sketch the voltage transfer curve, what we would do, we can obviously sketch it from the equation, but recognizing that stuff that we said was true up from ground becomes true down from VDD, we can also basically just flip our source follower, NMOS source follower characteristic which looked something like this. We can flip that around so that stuff that was true up from ground is true down from VDD on both axes. And so what the curve would look like is something more like the PMOS curve would look something like this. So this would be VDD minus VB and this slope would still be kappa. And so this is the NMOS version of the characteristic, and this would be the PMOS version of the characteristic. So what was true up from ground is true down from VDD and down from VDD. So up from ground would get us some x value here, down from VDD would get us a corresponding x value, up from ground, and the output down from VDD. Okay? So that is the NMOS and the PMOS source follower, and that is going to do it for this segment.